Welcome to Engineering Dynamics. I'm your host, Dr. Walk. In today's video, I am going to go through some kinematic relationships and integration properties. I'm going to go from acceleration to position. And I'm going to do that using a couple of examples. If that interests you, stay tuned. Okay, so for example 1, we have a small airplane. It touches down smoothly on a runway at 60 miles per hour. If it deaccelerates to a stop at a constant deceleration rate of 10 feet per second squared, find the required length of the runway. So this runway is going to be a straight line. That means we're working in rectilinear motion. We are given 2 points. We are given a touchdown. It's going to touch down and we're going to start our clock. So our clock starts at 0 seconds and our position is also at 0. We are touching down at an initial velocity. We are given 60 miles per hour. If you do that conversion, you should get 88 feet per second. Okay, so we can write that here. We have 88 feet per second. Time 2, I don't know. Position 2 is what I'm trying to find, but I do know that my velocity at the end of that runway, it better be 0 or I'm going off. Okay, so all I know is that I am given, and I also am given a rate of deacceleration. This does say a constant deacceleration, so I could run to those constant acceleration equations, but I'm going to go ahead and use the kinematic relations just for us to get used to it. So when we run into acceleration that's not constant, we know what to do. Okay, so we have acceleration is deaccelerating at a rate of negative 10 feet per second squared. So my kinematic relationship, I'm given acceleration, I want position, so I know I'm going to have to integrate this thing twice. So let's go ahead and start with our first relation, and we can relate acceleration and velocity. I am given acceleration, I want velocity, so I know I'm going to have to integrate this thing. So my first step is to separate variables. So I'm going to bring my t over, because acceleration is a constant, so I can put those two together. So I have negative 10 dt equals dv. My second step is to integrate this thing. So I'm going to integrate both sides. The integral of negative 10 dt is going to be negative 10 t. The integral of dv is v. And I need to evaluate this from t naught to t and from v naught to v. Okay, so this brings me to negative 10t minus negative 10t naught is equal to v minus v naught. Okay, so my v naught is 88. My v is 0. So I can automatically say, okay, this one goes to 0. And my t naught is 0. So I can reduce this equation to negative 10t is equal to negative v naught, which is 88. So I can actually put that in, it's just 88, right? So I can say negative 88. So I know that my time is going to equal 8.8 seconds. But that's not really what I'm looking for. I can bookkeep it and put it here because now I know that parameter at that second point. But I'm really looking for position. But we can relate velocity to position. Our kinematic relation states that, doesn't state that. It states that v is equal to ds dt. But here, well, let's keep going. So first we have to separate variables. Velocity is just going to be some sort of function in terms of time. So I just have to separate my variables. So I can put dt on the same side. is equal to ds. Now I need to plug in a function for that. And here's where a lot of confusion I find comes up. So let's take a look at what that function is going to be. And we'll do it in blue. So here I'm going to go back to this step here. Okay, negative 10t plus 10 times 0 equals v minus v naught. And I am plugging in my initial conditions because that's where I start from. So I'm always going to use my initial conditions. And my initial condition here is 88. So now this reduces to negative 10t equals v minus 88. So v is equal to negative 10t plus 88. Please note here, I'm going to put in my initial conditions, but not my final conditions. Okay, that's what I want the function to be. So include your initials. Okay, so now that I have this, I am going to plug this function into my relation. Okay, so I have v, which is negative 10t plus 88 dt equals ds, and I want to go ahead and integrate that. So the integration of negative 10t is going to be negative 10 divided by 5t squared plus 88t is equal to s. I'm evaluating this from s initial to s final and t initial to t final. Okay, so let's go ahead, and this is going to reduce to negative 5t, and so I'll just do t squared plus 88t, and this is going to equal s, because t naught is 0 and s naught is also 0. So I want to find s at t, and I found t2 at 88. I said that it took 8.8 seconds for me to reach a 0 velocity. So that means that at 0 velocity, that's where I'm looking for that s. So I'm going to plug in, I have negative 5, 8.8 squared plus 88 times 8.8 is going to equal my s value. So my s is going to equal 387.2 feet. At minimum, my runway has to be 387.2 feet at minimum. All right, let's try for example 2. So example 2, we're going to be looking at a gas gun, and a gas gun, basically we're looking at high velocity impacts, and I'm setting up my problem as a function right to begin with, and this is going to allow me to change the gas that I'm using in my gas gun. Okay, so let's walk through this. I want to assume that the acceleration of a projectile in meters per second is given by A equals CS, and this is in meters per second squared, where S is the position of the projectile in the barrel in meters, and C is a constant that depends on the initial gas pressure behind the projectile. The projectile is going to start from rest, so it is going to start, T naught is 0. It's going to start from rest, so V naught is also 0, but position, it is going to start 1.5 meters in that barrel. And it is going to accelerate until it reaches the end of the barrel, which is at a position of 3 meters. It wants us to determine the constant C necessary for the projectile to leave the barrel at 200 meters per second. So I don't know the final time. Okay, so I am given acceleration, and I want to find a constant C. Okay, so I do have lots of velocities, I do have positions, so that tells me that I'm probably going to need to use a couple of things here. But let's go ahead and start with our first kinematic relation because we are given acceleration, so that's a good starting point. So we know that acceleration is the derivative of velocity in terms of time. My acceleration here, this acceleration is not a function of time. This acceleration is a function of position. S is some distance, okay? C is a constant. So this acceleration, it's really an acceleration in terms of position. So I can't bring my dt over because it's not a shared, it's not like values, okay? It's when I say separate variables, the two don't match. S and t do not go together. So I have to multiply the top and the bottom by ds. So I'm introducing that variable that I want, okay? If we look, what is ds dt stand for? Remember your other kinematic relation, velocity equals ds dt? Well, ds dt, we can just replace with velocity. Okay, so now I can say A is in terms of position will equal velocity dv ds. Now it looks like I can group like variables, right? So now I have s's on one side and I have v's on one side. So I can say that as ds is equal to v dv. Now I'm ready for step 3, which is integrate. So let's go ahead and plug in what our A is. A was given to us as cs ds equals v dv. Now remember that c is a constant, so when I go to integrate this thing, I can take it out of the integral. So I can say c is the integral of 1 over s ds is equal to v dv, and I'm taking the integral of that. And I'm going from s naught to s, v naught to v, and the integral of this is going to be s1, actually it's going to be, I'm sorry, it's going to be the natural log. So I'll do the natural log of s evaluated as s naught to s is equal to v squared over 2 evaluated from v naught to v. Okay, so now I have c, the natural log of s minus the natural log of s naught is equal to v squared over 2 minus v initial squared over 2. My v initial was 0, so this term goes away. My s naught has a value of 1.5, so this is 1.5. My s final has a value of 3. So, and my v final has a value of 200, okay? So here I'm going to say that c, I'm going to work this out here. So I have c ln of 3 minus ln of 1.5 is equal to 200 squared divided by 2. And I can solve this for c equals 28.85 times 10 to the third meters per second, meters squared per second squared. And that is good because our acceleration is equal to c over s. S has a unit for position, which is going to be in meters. And our c has meters squared per second squared. One of my m's cancels out and I'm left with meters per second squared. So that checks out. Okay, so that was good. No tricky integration process there. So let's go ahead and move on to example 3. Okay, in example 3, I'm looking at a Scotch yoke, and what a Scotch yoke is it converts angular to linear motion or linear to angular motion, depending on how you're holding the mechanism. In this specific problem, it states that the acceleration of point A, so I'm looking at this point. That is a terrible color to use. I'm looking at point A, and it says that the acceleration of point A is defined by the relation A equals negative 1.8 sine kt. Okay, and it says A and T are expressed in meters per second squared and second respectively, and K is 3 radians per second. Be careful there, check your calculator when we go to do our calculations that you don't have it set in degrees, that it is in radians. Knowing that X equals 0, V equals 0.6 at time equals 0, so these are all your initial values. They want us to find our velocity and our position at t equals 0.5 seconds. So we are given acceleration. We want to find velocity and position. That means that I'm going to have to use 2 relations. So right away, I want you to put on your paper the relations I'm using is acceleration and velocity. Okay, so why don't we start with our acceleration? Our acceleration is a function of time, so I don't need to manipulate the equation by multiplying the top and the bottom by anything. So I'm just going to say that A, which is negative 1.8 sine kt, is equal to dv dt. My second step is to group like variables. So I have negative 1.8 sine kt dt is equal to dv. Now my third step is going to be to integrate both sides. And I'm going to integrate from t naught to t and from v naught to v. Okay, so my integral for this, I'm going to have I have to use u sub, but a lot of times I think people just understand that they have to take the k out and divide. And my integral of sine is negative cosine, so my negative is also going to go away. So I have 1.8 divided by k cosine kt. I'm evaluating that from t naught to t equals v from v naught to v. Okay. Okay, so let's go ahead and try to work that out here. I'm going to change colors. You'll see why in a minute. So I'm going to have 1.8 divided by 3 cosine of k. Our final t is 0.5. Our final t is 0.5. So I'm going to say 0.5k minus 1.8 divided by 3 cosine, and our initial time is 0. So 0 times k is 0. This is going to equal our v final minus v initial. V initial is 0.6. V final I don't know. I know cosine of 0 is 1, so this is 1. And I know k is 3. So let's go ahead and clean this up. We have 1.8 divided by 3 times the cosine of 0.5 times 3, making sure your calculator's in radians. I should get a value of 0.04244. Wow, that's way too many significant sig figures, but you get where I'm going. And then you're going to minus 1.8 divided by 3, which is going to be 0.6. I have to make sure that I take this guy over, so I'm going to add that. 0.6 equals v. That means that v2 is equal to 0.424, that's fine, meters per second. So this is my velocity 2. I can go up here and I can plug this in. So my velocity 2 is now known, and it is equal to 0.042 meters per second. But I still need to find position. So now I'm going to be looking at my kinematic relationship, velocity equals the derivative of position in terms of time. So I need to get that velocity function. So we're going to go down here and we're going to try to get a function out of this. Remember that in your functions, you're going to leave V2 as a symbol, and you'll plug in values for your initial values. So your final values stay as letters, like parameters, and your initial values will turn into numbers if you have them. Okay, so my function, if I'm looking at this here, my function is going to be 1.8 divided by 3 cosine of, that would be t, so kt. Then I am going to say minus, this portion here is an initial value, so I can always include my baseline. So that's just going to be 1. That's going to be minus 1.8 divided by 3. And then again, I'm going to include my baseline. So I'm going to add 0.6 is equal to v. So I can reduce this function a bit to say that v is equal to 1.8 divided by 3 cosine of kt. Negative 1.8 divided by 3 is negative 0.6. So these terms are going to cancel out and leave you with this as your function. Okay, so now we're going to plug that function into velocity equals ds dt. So my velocity is 1.8 divided by 3 cosine kt dt, because it's as my velocity is a function of time, so I can bring that variable over to ds. Okay, so my next step is to integrate this. So I'm going to integrate both sides, and I'm going to go from time initial to final to initial position to final position, what I'm looking for. So if I take this integration, give myself some room here. If I take this integration, I'm now going to have 1.83, that's my constant. The integral of cosine is sine. Kt, remember you have to divide by k, so I'm going to throw a k out here. And I'm going to evaluate this from t naught to t. And this is going to equal s from s naught to s. Okay, so now I have t final was 0.5 seconds, t initial is 0, s initial is, I can't remember, s initial 0, okay? So that's going to be 0, and I'm looking for this guy. Okay, so now we can go ahead and plug in some values. I'm going to have my first one is 1.8 divided by 3. K is 3. Sine K again is 3. My first T is 0.5. Minus 1.8. 3 times 3 sine K times T initial is 0, so sine of 0, and is going to equal S final minus S initial, which is 0. So sine of 0 is 0. So this term goes away. Now I'm left with 1.8 divided by 9 sine 1.5 equals S. So S is going to equal, if I do 1.8 divided by 9 times sine of 1.5, is going to equal 0.1995. And that is going to be in meters. So if we go back up to our question, wants to know where is A moving? So I actually have a little, I don't know why I have one of these. Okay, I have a Scotch yoke here. Okay, so what I'm asking you to do is look at a point here, and I want to know if it starts, say, here at 0 seconds. In 0.5 seconds, what distance has it traveled? And you're telling me it traveled 0.1995 meters. Okay, so I hope that clears up a few things. Let me see if I have any more examples that we could try. We do have a parachute. All right, so in this example, we're saying that after deploying its drag parachute, the airplane's acceleration is given as a equals negative 0.004 v squared, where velocity is in meters per second. It wants us to find the time required for a plane to go from an initial velocity of 80 meters per second to a final velocity of 10 meters per second. So I'm going to say that my initial time, right when I deploy it, is 0. My final time, I'm not sure. But it does have a function here. Okay, so this is what I have. Let's see what I need to do to figure out kind of how to get... No, oh, I'm sorry. Final time is what I'm looking for. I deploy it and I want to find how long does it take to go from 80 to 10 meters per second. So that's what I'm actually looking for. So this is good. How do we relate acceleration, velocity, and time? By our first kinematic relation. A equals the derivative of velocity in terms of time. So my acceleration is given to me as negative 0.004 v squared. And here I can say, okay, my acceleration is in terms of velocity. So I want to get my both v's on the same side. So I'm just going to take dt over and I'm going to divide by my velocity. I can also leave, just for convenience, I could leave the 0.004 negative on this side. And I can divide by v squared dv, and now I'm ready to integrate. All right, so let's go ahead and do that. Let's go ahead and integrate both sides. And I'm going to integrate from t initial, which is 0, to t final, which I don't know. And then I'm going to go to v initial, which is 80, to v final, which is 10. All right, so let's do that. Let's have, all right, what is the integral of negative 0.004 dt? It's going to be t, and you're evaluating at t and 0. And this is going to equal, what is my integral of 1 divided by v squared? If you forget how to do this, this is basically the integral of v to the power of negative 2. And we can say that this is equal to v, you do negative 2 plus 1 divided by negative 2 plus 1. This is going to equal v to the negative 1 power divided by negative 1, which is going to really be negative 1 over v. Okay, so this is going to be negative 1 over v final minus negative 1 over v initial. Okay, so and then now I can plug these numbers in as well. So my t, my final t is actually what I'm looking for. So I have negative 0.004 t is equal to negative 1 divided by my final, which is 10, plus 1 divided by 80. This is going to give me a t of 20 seconds. So it is going to take 20 seconds for my plane to decrease from 80 meters per second to 10 meters per second once I deploy that parachute. Okay, I think that that's a pretty good review. I hope this helps. If you have questions, leave a comment below. If not, I will see you in my next video.